All right, guys, here we go. All right, so I know some you guys are gonna have this like urge to talk to each other because you're sitting across from people and it's just rude not to look at them and talk. So, and when I say talk, go for it. But when I need you, I need you. Okay. So because they caught up a couple minutes from us, I'm gonna roll through our notes, not too quickly, but it's gonna be somewhat redundant a couple of times. So I want to make sure I'm emphasizing the main points. If I'm emphasizing something, it's because it's a very common misconception, and that misconception. If I tell you up front it's a misconception, I'm like, hey, this is really important, this is a big point of confusion, then star it, underline it, make it bold, highlight it, something in your head so that you're very aware that that's like something easily confused, okay? So here we go. I want you guys to give me some thoughts, and I'll add to it and kind of clarify from there. Ooh. Okay, so let's call this one over here galvanic, and this one electrolytic. Emily, give me something cool about galvanic cells. Say what? They're thermodynamically favorable. Good. And that means delta G is positive or negative? Negative. All right. So we're going to keep, we literally see delta G basically every unit. Not from here on out, but like probably half of our units. Okay, so delta G is related to everything we do. So contrast that, Gigi. Right. So that means delta G is positive. Good. So galvanic cells run spontaneously, meaning they're thermodynamically favorable. In the what direction? Forward, right? Every single time we talk about thermodynamically favorable, it's speaking of the reaction and how it is written. And I know that we now know, hey, there's reversible reactions. We will never ever, and you have never ever, actually reversed the reaction. Like we may compare a forward reaction and a reverse one and go, oh yeah, 1/k now because we flipped the directionality of it, but we ourselves never flip things. So some of you guys are asking questions on the test like, should I flip this if it's talking about the reversible? No, we've never ever flipped anything. So thermodynamically favorable in the forward, non-thermodynamically favorable in the forward. So does this require energy to begin? No, so it requires no stimulus to start the reaction. It's going to happen on its own. So then how does that compare over here? Yes, it does, and it requires a certain type of energy. Does it require chemical energy or electrical energy to begin? Good, electrical. So it actually does require energy to make the battery flow. It's kind of interesting. Requires electrical energy to begin. Okay, give me something else. Fatima. Maybe some at your table.
Two half cells.
Which one? Galvanic, good. So galvanic cell are two half cells or two chambers. And those chambers are connected how? Anybody? Good. Okay, so connected with a salt bridge. All right, so contrast that, please. Or anybody who's ready? I'm moving on. Anybody who's ready here? This is a single chamber. All right, quick, can you tell me anything about that single chamber? It does. Both of these are in solutions. You're right. But I'm going to say this one's divided into two sections by a porous barrier. It's not like a one half connected with a porous kind of filter paper, which is what a salt bridge is. So this is a single chamber with a porous barrier. And that porous barrier means that they are able to flow back and forth between the two sides, but they're not technically separated. All right, I didn't mean to mention this up here with our delta G negative and our delta G positive. JT's table, tell me what K values would be here for this one over here. K what? Greater than 1, so it's thermodynamically favorable in the forward direction, which means products are favored. And then over here, K is less than 1, meaning it's thermodynamically favorable in the reverse direction, meaning reactants are favored. Megan, you got something to add here? Okay, so an example of this could be electrolysis. An example of electrolysis is water being electrolyzed, meaning it breaks down to its two individual elements, which would be wet and wet, hydrogen and oxygen, and I think we need like that. So water does not naturally break down on its own. It's not favorable to occur. If not, we would have no water, right? It would just be breaking down into hydrogen and oxygen, and we wouldn't have that to sustain ourselves, but we actually would have a lot of energy because of that. Regardless, though, that is an example of electrolysis. Anybody with E cell, like the electromotive force, the value, is it positive or negative for galvanic? Positive, good. E cell is positive here, so E cell is negative here, okay? So what we should find as a correlation between these are delta G value negative, K value greater than 1, E cell positive. There's actually an equation that brings a lot of these together. We'll speak to that equation a little bit more later. And so then the opposite is that for the non-spontaneous ones, so for the non-thermodynamically favorable electrolytic cells. And they're positive E cell, or sorry, positive delta G, K value less than 1, and a negative E cell. So those are like the three big things you should know about each of these. What is one commonality? What do they both involve? Anybody? Yeah.
Producing useful electrical energy.
Okay, so somehow making electrical energy are involving electrical energy. I'm actually going to say like electrical versus chemical, because both of them have a relationship to chemical energy as well. There's one more thing. Yeah. Okay, so they both have, actually there's three things. They both have an anode and a cathode. And it says anox and red cat because now we should actually understand there's one specific process that occurs in the anode and one specific process that occurs in the cathode. Anode? Anybody? Oxidation, right. So this is an oxidation. Oops. There's oxidation always occurring at the anode. I don't care if it's a galvanic cell or if it's an electrolytic cell. Oxidation occurs at the anode. And the way you can remember that is A is a vowel and O is a vowel. Okay? So then everybody, what happens to the cathode? Reduction. And how do you remember that? Okay, red cat or the consonants, yes. Okay. So, of course, now we realize the very big commonality between these are that redox reactions are the heart of batteries. Redox reactions are the heart of how a cell will run in a favorable or an unfavorable direction. So with respect to that, with oxidation reduction, just a quick reminder, what is oxidation? Loss of electrons, and then reduction is gain of electrons. Good. So the first part of this is review of redox, which is really good before your midterm because that's not something that you'll actually probably review on your own. And then the second part of this is more batteries. So just some quick housekeeping things. You guys got your holiday review, yes, last week? So what I'm looking for is half of this to be done by 1/2, so January the 2nd. The other half is due the day after our test, which I think is the 10th. So I think our electrochem test is the 9th, and so this is due the 10th. I can double check those dates, but half of this is due, and then the next half is due. So what I've done is I've set 2 days before our midterm, because our midterm is on exam day, which is January the 12th, because that's the only time I have you for 3 hours and some change. And this will be a full-length AP exam, which is 3 hours and some change. But I will not get that graded before grades are due. Absolutely will not. That is your first grade in your third quarter. Okay, so one, that helps you know where you stand for second quarter, but two, that could like not make you or break you. Like it's going to be your first grade of third quarter. So when I put those in, just don't look at your grades for a while. Just hang out, okay? So I'm just telling you that because like if it's not where you want to be, you've got the whole third quarter to make a difference. Like there should be no stress over that. But I do want you to do well in your midterm, and I want you to get the experience because that's one of the only times I'll have you for that length of time. Like literally is the only time I'll have you for that length of time, which will put you in the experience. Is this a good question?
Yeah.
Yeah.
Midterm counts as test grades.
Counts as 2 test grades.
Okay.
Yes. So what I'm thinking of here is with the unit reviews, I did say exempt. If you look on the holiday packet, exempt Unit 8, because Unit 8 used to be acid-base equilibria. It still is, but I knew that we would not finish that before midterms, and equilibrium for like another month of your life is torture. So I'm switching that to be right after midterms. So where it says Unit 8 in here, we have not discussed that. Please go ahead and put an X through that. So you have 7 units to do, where there are 5 multiple choice and 1 free response. Do you see this? 5 multiple choice and 1 free response. So I would do like all the multiple choice one day. That's what, 35 questions? That's not that long. Okay. And then we'll check them in class and then go through some of the free response on your own time. But the idea is that you're spending a little bit of time for review over break, and then we'll have 2 days for midterm review, and then we take our midterm. Question? I want you to try those. There's a video of coordination compounds, which is complex complex chemistry. We did discuss those a little bit before our alum lab. So if you need to look up some of that information, it's there for you, but we should just be aware that there's something called coordination chemistry out there. Okay? But at the very end, do you see it's like ACT-based practice? Do you see that? So those actually are really easy questions. I think they're easier than the AP questions. But where it says like right after Unit 8, these are practice graphical analysis and data analysis published in ACT. Okay, so some of those are quite easy, but they also give you some prep for ACT-based stuff too. Who still has to take the ACT? You already took it like in junior year. Or no, they get you in March. That's why I did that. Helping you out here. Okay, I mean you're good. But okay, so that's housekeeping for now. We ready? Okay. So, in general, electrochemistry is one of the coolest subjects we'll talk about. There's a lot of real-life applications. One is just batteries in general. So we talk about electrochemistry with respect to redox because redox runs electrochemistry, but just making a battery is what this is really representing. But we'll have to understand that just electrons flowing is what electricity is. Okay, just electrons flowing. But how do electrons flow? From what to what? Anode to cathode, because the electrons lost are from the oxidation and the electrons gained are to the reduction. So there's one flow. It's from oxidation to reduction or from anode to cathode. And so we have to always relate that back to redox as much as we can. So I'm going to show you a quick scene from a show. Who has watched Breaking Bad? Okay, so if you have not, spoiler alert.
Out of the last 2 sponges. Remember the electrolytes? Huh? Well, think about it. Battery is a galvanic cell. It's no more than an anode and a cathode separated by an electrolyte, right? Right.
Chemistry teacher, not great student.
On one side, you have mercuric oxide and graphite from their brake pads. This is the cathode, the positive terminal. This is where the supply of current flows out from, see? And here, I'll show you. On the opposite side is our anode. This. It's zinc. What we find in our coins and anything galvanized.
So they're stuck in the desert.
So the sponge is the electrolyte?
Yeah, well,
And the RV.
potassium hydroxide is the electrolyte.
Where they have
Yes,
illegal things going on.
soaking the sponges. But good hand. What shall we use to conduct this beautiful current with? What one particular element comes to mind?
Wire.
Copper.
Wire's not an element. We didn't know that.
Copper. The only question now is, will this supply enough current? And how many cells will we need? We've only got material enough for 6.
So they're trying to make these batteries cells, right? Anode, cathode, and a supply of electrons to repower their dead battery of their RV, which they're entrepreneurs in this case, so they are making some substances to sell. But they're trying to then make a circuit to supply the energy that the battery needs to restart. So thought that was kind of cool, and when I saw that, I had to show that to you guys. Yeah, I've saved this for like 5 years. It happened. Okay, so review of redox real fast, and you definitely write down what you need to. We're just going to do a quick review before we jump into the electron. So oxidation is loss, oil. That's how we remembered it in the past. Reduction is gain, which is gaining of electrons. So we're speaking to the transfer of those electrons lost to another side, which would be gain. These have to happen simultaneously because there's no place for the electrons to flow if they are not gained by something else, so they are a coupled reaction. Electrons move from the Ra to the OA. What's Ra stand for? Anybody remember that? Reducing agent. So the reducing agent is the thing that is what? Okay, so this is the one that is oxidized, and the oxidizing agent is the one that is reduced. So we'll sometimes still use that terminology, like on the reducing agent, you're the oxidizing agent. We know that is actually flipped with respect to what process is occurring. So that's just a little bit of review there. And we will also do a quick review of balancing and half reactions, like in acid and base. So that's been a while. Do you remember that? Adding H's on one side, O's on one. Okay. So with, I'm going to try to show you this without showing the answer. With this half reaction, X yields X plus and E minus. So electrons being, what's happening to electrons? Is it being lost or gained? One or the other. Let's make a choice. It's being lost, right. It is being, from this guy, that is releasing an electron. So this is a what type of process? Oxidation. This is an oxidative process because its X is losing an electron. So what's happening to its oxidation state? It's getting what? So it's going from what to what? 0 to plus 1, so it got larger, right? So that shows a loss of electrons because the oxidation state went up. Okay? And then this other, so I mean, electrons in the products mean what's happening? Oxidation, right? Okay, so then you can see the same thing, a -3 to a -2. What happened to oxidation state? It went, no, it went up. -3, -2, -1, 0. So that number line is actually negative to positive, so this is still going up. So then the next one, +2 to a +1, what's happening? Reduction, so it's gaining an electron, and you can see the oxidative state change as well. So if electrons are in the reactants, that means what process is occurring? Reduction. So that's an easy way to identify by just looking at the half reaction if oxidation or reduction is happening, but you should also be able to rationalize it with the oxidation state changes. Are we good here? Okay. So if the electrons are in the reactants reduced, that's pretty easy to remember as well. Okay, so we know that we have all these oxidation states. Give me a couple that you remember. Now give me one. Like where we assign oxidation states, there's like a priority list that we deal with. No, not names. Like if I gave you a free element, what's its oxidation state?
Like magnesium is, or not, like sodium is 1, right?
That's only if it's sodium ion. If it's a free element, meaning not ion form, what's its oxidation state? 0, right. Free elements are 0. If they are an ion, that ion charge is its oxidation state. What are some others that have like priority over others? Oxygen generally gets a -2 unless it's paired with fluorine, because fluorine is going to win that electronegativity battle. So in terms of electronegativity, it flows up and to the right. So fluorine's the most electronegative. Hydrogen generally gets what? A +1, unless it's paired with something that would give it like a -1. It could be a hydride, which is an anion. So these are your few reminders. Free elements, meaning they're elemental, not an ion, will be 0. And I say almost always because we have those few instances where they're not. +1 and -2. So this example, OF2, oxygen or fluorine gets the -1. That's like the priority. So -1 and a -1 collectively make a -2. So what's oxygen's oxidation state here? +2, right? Which is very rare to see. In hydrogen peroxide, we also have an odd situation. Hydrogen getting the +1 because that's priority. What does oxygen get? A minus what? -1, right? So a +2 and the -2 neutralized to make it a 0. So that again is another instance where oxygen is not a -2. Those are really the only two that you have to know. Overall, the charge on the compound, like in this example, the overcharge is 0. So that's why these oxidation states add up to be what? 0, right? It's showing a non-charged species. But if we have a, like, sulfate or something, then sulfur plus oxygen will equal -2. So the overall charge of this species being -2 will equal the overall charge on each of the elements. So as a quick reminder, the oxidation state is governed by electronegativity. So electronegativity runs up and to the right. So that's why we always artificially assign an electron, or if it's in a covalent situation like here and here, we assign who would have an overshare of the electrons. We assign that to that element. So that's why fluorine gets the -1, because it is the most electronegative element and it can only gain 1 electron. Good reminders? Okay. And then this is just a graph. That's not really that important. Okay. So let's track this change. First of all, what kind of reaction is this? Single replacement, good. So what's the oxidation state on this magnesium?
0.
Okay, keep going. Silver is 1+, and here's one way to think of it. This is silver and this is nitrate, right? Collectively together, they complete each other with their individual charges. So what's nitrate's charge? -1, so what does our silver's charge have to be? +1, and we know that because that's technically an ion. That's silver ion, 1+. It's just combined with nitrate. So collectively, nitrate's a -1, but as a whole, this is 0. So oxygen has to be what? -2. What is nitrogen? No, +5. You guys are good. So this is nitrate being a total of a -1. You can think of it as 3 times a -2 is -6. -6 plus something equals a -1. That's a +5. Or total -6 plus 1 gets me to -5. +5 will cause that to be a neutral compound overall. You think of it as either way. If you want to split it into ions, that's fine. Okay, keep going. This one? This one? Anything here? Magnesium is a +2 because that is this ion form, and normally we do assign oxygen first, so that's a -2. This is -2. What's nitrogen? Say again? +5 again. Good. So this being a -6, this being a +5, but there's 2 of them. That leaves us with a -2 overall here. +2 cancels it out. So we're working it out together. Okay. So who are the 2 species involved in oxidation and reduction? Magnesium and silver. So what's happening to magnesium? Losing electrons, so oxidized, good. And then silver, +1 to 0. You're right, it's gaining. And it actually, you see there's a 2 and a 2 here. So each silver gains 1 electron. There's 2 of them, so there's an overall net change of what? 2 electrons. And we have to have that, because if not, we have lost electrons someplace and there's no charge balance, which we cannot lose matter. It's not allowed, okay? So this is reduction. Okay, so nitrate's just big chillin', it's a spectator anyway. So we know who's oxidized, magnesium. We know who's reduced, which is silver. If you had to write those half reactions out, this would be magnesium yields what? Magnesium 2+ and 2 electrons, right? Electrons are in the products, means it's oxidized. And then this would be what? Silver what? Plus, I'll put 2 of them there, okay. 2 silver 1+s and 2 electrons yields silver solid, right? We would see that as like a sparkly kind of silver appearance. This one doesn't really, it's just silvery. Doesn't really have a cool color, like a nature to it. Okay, oops, didn't mean to do that. If these reactions occur spontaneously, meaning thermodynamically favorable, who's the stronger reducing agent? I hear like a couple answers loud and proud. So reducing agent means what? It's oxidized, okay? So magnesium is the one that's oxidized, meaning magnesium is the stronger reducing agent. So if we had an activity series from high to low, where would magnesium be? High or low? Yes, higher than silver. So in our activity series, we would have magnesium up here and silver down here. Because the higher the activity series means that you're more likely to what? not just react. There's a specific, like, is it oxidized or reduced? Because react is not an informative term. Oxidize, right? Active means to oxidize. Active means to give up electrons, which is why it makes it so reactive. So who's highest on the activity series if you had to think about it from the periodic table? Say again? Who's like so willing to give up electrons, not even funny? Somebody in group 1, right? Somebody in group 1. It's probably actually going to be lithium, because lithium actually, though it is small, it is willing to give up its electrons. Francium is large and it's more willing to give up electrons, but there's an interplay between the size and the effective nuclear charge and also the present, like what it's in the presence of. So basically group 1 metals are going to give up their electrons quite easily. Okay, so remember our acid-base rules. What do we always start with? Like this is like balancing an acid, balancing a base. Write the reactants out. Good job. Keep going. Half reactions. Okay, and then balance the non-O's and H's. Okay. I'm just going to scroll down here. Okay. So write your half reactions. Balance everything that's not O and H, because those are like might be chromium or a carbon or something that's non-OH. And then how do you balance out the oxygens? Adding waters. How do you balance out the, this is in the presence of acid, right? So how do I balance out the H's? H plus, because that's in the presence of acid. You have a lot of H plus floating around. And then once you balance those, finally you balance charge, right? So you count up looking at the charges that you've assigned from one side to the other. Let's say it was a 12 plus on the reactants and a 2 plus on the products. 12 plus and 2 plus, where do I add my electrons? Well, no, I have, where do I add my electrons? I haven't even added electrons yet. Wait. Okay, you add it to the side, that's 12 or 2? 12, right? You add 10 electrons to get the 12 plus down to a 2 plus. And then once you compare those two half reactions, you decide if they're balanced electrically, meaning their electrons, and then you can simplify the overall reaction. Okay, we're going to practice with that. What's the only thing different with base? Well, do I follow the same procedure? Yes. When do I start adding OHs? Right before I add both reactions together. I actually need to balance my charge. Like, balance your charge first. Don't mess with the charge. So how do I know how many OHs to add? How many H pluses you have? Do I add just to one side or do I add to both sides? I add to both. So if I add 10 OHs to one side, I add 10 OHs to the other side, because after that, if I only add 10 OHs to, like, say, the reactant side, what have I then done? Totally change the charge. So I can't have a charge balance. So if I add it to both sides equally, it's not going to cause a problem with my charge balance. So I've just copied that, and then I just put the little red right here to give you an indication on when to do that. The board is out. There we go. So after you've added your OHs to the H pluses on one side, you do it together. You can also combine the H's and OHs to make water. There'll be some simplification processes at the end of that. But I would say 75 or 80% of the time we see acids, 20 to 25% of the time we see bases. But we should still be comfortable with that. It's right there on the back lab station, Andrew. Thank you. Can I go past this? We're going to do a practice one, okay? Do you want to balance this one? Yeah, let's balance this one real fast. Okay, so start me off. What's my first step? I heard half reaction. What's the first one you guys want to do? Permanganate. Remember, put your ions. A lot of you guys, I'm just saying, you get lazy. You don't want to put the 1 plus or 1 minus because I don't know why, and then it would mess up your charge balance again. So permanganate yields manganese 2 plus, okay? Just drop it on the back lab station. Thanks. Okay, so keep going. What's the other half reaction? You guys have paper, Miriam?
Can you grab a bundle of white paper down here? Sorry, you guys balance that for a second. Have some.
Alright, sorry, what's the other half reaction? Acylic acid, carbon dioxide. Okay. For the first half reaction, are the non-H's and O's balanced? Are the non-H's and O balanced? Manganese and manganese. 1 and 1. Yes, we're good. Okay, so now what do I want to do next? I want to add options through the presence of water, which to which side? Okay, so how many do I add? 4 waters, because that balances out 4 O's and 4 O's. Marcus, back lab station. Okay, keep going. What's next? So there's 8, so 4 times 2 is 8, so add 8 H pluses to the product, to the reactants, and then now all the atoms are balanced. What's next? Charge balance. So what's the charge over on the reactant side? 7 plus. On the product side, 2 plus. So 7 plus or 2 plus, who gets the electrons? And how many do they get? 5. Okay. Bottom. Good. Adding a 2 first, because that's the part everybody forgets, is to balance the non-H's and O's. And then good. O's are balanced naturally, so there's 4 and there's 4. So the waters are fine. And then you guys said add 2 H pluses over here. Okay. So now to go to charge balance. And so there's a net of 0 on the reactants and then a net of 2 plus over here. So Kui, what do I add? 2 electrons. Okay. Now what's your next thought? Why am I multiplying? Why am I multiplying again? I need to have electrons balanced. I can't have 5 electrons gained in one and only 2 lost in the other, right? That's not how that works. There needs to be the same electrons lost and gained. That's why that's the reason I have to balance. So I'm going to multiply the top one by and the bottom one by. Okay? So we know that's going to cancel out 10 and 10 electrons. Those are canceled because they are gained and lost in the same ratio. So finish this up for me. I'm going to do the top reaction first, if you guys don't mind. 16H plus 2 permanganates plus, okay, so 5 oxalic acids yields 2 manganese ions and 8 waters and 10 CO2s and 10 H pluses, and then the electrons I've already decided they cancel. Okay, simplify. So this H plus and those H pluses can be simplified. So we say 10 are gone, but then how many are left over here? 6. Everything else is good. Is it coming back to you some? It's been a while. This is good review too before you do your holiday, so you're not like on a struggle bus. Give me a thumbs up whenever you're done with that. Okay, the next one is more of an FRQ style one, because I know I have some time with Electrochem. I have one extra day that I'm playing with, so I want to make sure we're reviewing some like redox now, especially with like redox titrations. So the redox titration, what do you start off with? Like, anytime you ever do a titration problem, what do you always have to write first? The balanced chemical equation, right? Which redox balancing is just a little bit more, like we have here. And then, what do you start with in terms of doing the math? Say again? The molarity of the known. Multiply the molarity by its volume. You get to moles. You get to moles of the other thing. You move on, right? The same process applies for every single titration. That, especially if you're a KSP1, if you need some help, please stay after school today or tomorrow. Okay, so I'm gonna scroll down some as I move, but I want you guys to write down the givens. Read that first and write down the givens. This is a case where somebody was pulled over and they were trying to see if they were intoxicated, see if their blood alcohol percent level was too high. Write down your givens. William, give me start on the first half reaction. Mm-hmm. So you took potassium dichromate, but immediately you did what? Okay, so but what did you do first with potassium? Did you include the potassium in the half reaction? Okay, if you did, you're probably going to cancel it out because a lot of times our group 1A metals are spectator ions. So let's exclude the potassium, just have the chromate or dichromate. So dichromate yields chromium 3 plus because it tells it to you right here what to expect. Okay, and then you said you went ahead and put the 2 there because you saw the 2 for chromium. Okay, well let's keep going on this. What do I need? Somebody. 7 waters and 14 H pluses because I had 7 times 2. And sorry, this does not say an acid. If it doesn't give you indication, please assume acid because that is our predominant case. Keep going. What's my charge? Good. A lot of you forget to multiply this 3 by 2. So there's 14 minus 2. That's a positive 12 on the reactants, a positive 6 on the products. Where do I add my electrons? To the reactants. Good. So there's 6 electrons that need to be added there. Okay. JT, what's the second half reaction? C2H5OH yields, say again? Carbon dioxide. Okay. So that was given here, and it said it produces carbon dioxide. So there's information given to you. Miriam Shopkeeper. Thanks. All right, so there's information given to you in how to predict those products without any questions. All right, guys, what's next? 2 in the front, good. 2 chromium or 2 carbons, 2 carbons. How many H2Os? So there's 4 O's. So where do I add them? I'm balancing O's. We always do O's first. To the reactant. So there's 1 O, there's 4 O's, so I need to add what here? 3 H2Os. So now there's 3 plus 1 is 4 oxygens. And then what? So there's how many here? 6 from here, but also 6 from here. So that's why we have 12 H pluses over here. And then so this is all neutral on the right on the reactants, and so on the right we have a positive 12, so we need 12 electrons to cancel that out. Okay, charge balance. Multiply by 2 up here. Okay, so this is going to get kind of messy. Try to simplify as much as you can right now. I'm sorry, bring them all down and then try to simplify. I'm just going to make myself some room. So, what are you guys simplifying? I heard the H pluses, which means you're doing what with them? So there's no more 12 over here. And what's here? 16 H pluses. Keep going. So subtract the 3. So there's no more than 3 waters here. And what's here? 11. Everything else is good, right? Okay, so 11 H pluses, blah, 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 blah. 11 waters are really what we have changed. Okay, there's our balanced chemical equation. Next, in a given case, 35.48 mils of 0.05182 molar potassium dichromate was required to titrate 50.02 grams of the blood. Assume you only have the ethanol only reacts with the potassium dichromate like nothing else in the blood for like some reactions. So identify the oxidizing and reducing agents. Well, let's first do that based on the half reactions. Shout them out. So is dichromate oxidized or reduced? It is oxidized. Oh, is it? look where the reactant, or look where the electrons are. Right. So remember, the electrons being in the reactants mean that this guy is what? Reduced. It gained 12 electrons total. Like it gained 12 electrons. Like itself is reduced, so it's the oxidizing agent. And then the other active species here is ethanol. So it is what? So you can see it lost 12 electrons. So itself gave away 12 electrons. So this one is oxidized, so it is the reducing agent. Okay, so you do have to think. You can't just jump to the chase on that one. You do have to like think through what's happening. It's not one that you just immediately think of. All right, so how many moles of ethanol were contained in this blood sample? So, given the information, what do you guys want to start with? Ooh. 35. I'm just gonna, let me just erase this question because I need some space. Okay, 35.48 milliliters of what? Of some species, right? So this together, when I multiply them together, what will I get? What units? Millimoles, technically, right? But I'm going to go ahead and take this to liters. So what is this in liters, guys? 0.03548 liters times what? 0.05182 moles of potassium. Yes, we have to write potassium here because this is a like net species or net compound. Potassium dichromate per liter. Okay, so liters cancel. Now I'm in moles of potassium dichromate. What do I need to do next? I need to get to just dichromate, right? That's what you meant. So just dichromate, what's the ratio from potassium dichromate to just dichromate? Say again? 1 to 1, right? There's no extra subscript behind dichromate. So in 1 mole of potassium dichromate, there's 1 mole of dichromate ion. Okay? The question is getting to moles of ethanol. So what's next? Using the Found's chemical equation, I get the mole ratio, right? So give me that mole ratio. 2 to 1, right? There's a 1 in front of ethanol. So 1 mole of ethanol, I don't know why I wrote ethanol, not the chemical formula, but it already happened. 2 moles, my marker is off by like an inch, so forgive me, it's getting kind of interesting up here. 2 moles of dichromate. Okay, we got some moles of ethanol. Calculate. Any takers? Say again? 9.19 times 10 to the negative 4th moles of ethanol. Can I get a thumbs up if you also got that? All right, Ms. Disorder. Okay, I didn't get a chance to do that yet. Okay, so that's the moles of ethanol. The second question, or third, fourth, was the person legally intoxicated? So we have the idea that intoxication is 0.08% by mass. So how would we approach this? Take the moles of ethanol to grams and then divide it by the total blood sample, right? So that's my total blood sample. What we're looking for is the alcohol that's present in the blood sample, which is going to then give us the percent by mass of their blood, which is alcohol, which we're hoping they're good. Let's see. Okay, so we're going to multiply this by, what's the molar mass of ethanol? 46 246.08. You say that questionably, Gigi. I believe you. Okay. Can somebody give me that, those grams? Grams? Say again? 0.036. Okay. So 0.04236 grams of ethanol. We're going to take that and divide it by their blood sample, which was 50.02. 50.02 grams total sample. Like any percent, it's always part per whole, so that's how we need to do that. Times 100, and what's their blood alcohol content? 0.08 what? 5. Lock them up, people. We're above the 0.08%. Okay. So that's a quick review of technically how redox is involved in real life, which is interesting, but also how we take a redox and do a titration. We run it the same way we do all titrations, take the knowns to go to the ratio, move on to the next step, and then also how we can perform percents. So like in your redox test, we did a percent like metal per ore. So or like, you know, how much iron was in a metal ore sample. That's the same thing. We did part per whole. Okie dokie, moving on. Okay, electrochem. I have a lot of redox review. I'm gonna skip this for a minute. And here we go. Okay. So with electricity, we are speaking of redox reactions, which is why it's important to have that background. But we also have to understand that it's just electrons moving around. So if electrons are going to move, they're going to move in a favorable direction. And they actually have the reason behind moving electrons is called electrical potential differences, or just potential differences as it's kind of shortened to. So the stuff in like blue, purple, and then underline, electrons are going to flow in response to our potential difference. And those potential differences are called voltages. Let's start with that. I have like 15 minutes left for today, so I know it's gone by. So I'm going to make sure we spend some time on batteries tomorrow. So once these electrons, so the purple stuff is what I would be kind of writing here, okay? So once we have this electrical potential difference, electrons are flowing. We like to measure how electrons flow. We want to know how fast they're flowing, like how many are passing per minute, so we quantify that into something called a current. We've all heard of current before. So an electrical current is the amount of electrons that pass, or actually their net charge, per time. And that measurement, that unit that we measure current in, are called amps or amperes. Who's ever heard of amps? Amperes. Okay. So the charge, or the unit for electrical charge that we usually refer to electrical charge as is coulombs. And since we're measuring it per time, it's coulombs per second. So C stands for coulombs. And you read a little bit about that in your reading. So to summarize that once again, electrons flow in response to a potential difference. They flow in a favorable direction with no intervention needed, no jump sparking, there's no push of electrons. It's naturally going to occur in a galvanic cell. And as they flow, we measure how fast they flow by measuring their charge that passes a given point per time. That charge is measured in a unit called, that charge, specifically the charge is the charge of a set of electrons. Coulombs is a unit of charge, but when we put that charge per time, we call it a amp, right, or an ampere for long. That's amp is for short. And I've kind of drawn just a general setup over here. We actually have to have an external wire, which you guys read about as well. The external wire is how we actually capture those electrons because they flow from one side to the other through this galvanic cell setup. So the wire has to be a conductive piece of metal or like graphite, something that's going to be conductive. If not, it will have resistance to flow. So this is your background, and some of this we did speak to, and I just actually just said that. So some of this we did speak to in our Venn diagram warm-up, but as some reviews, galvanic is going to have a spontaneous flow, and they actually convert the chemical energy, like from the elements themselves. We convert chemical energy into electrical energy. Some of you guys are checking out on me. Is it because we're reviewing again? You gotta stay with me, okay? So we have to convert from chemical energy to electrical energy. That is one definition of galvanics you should be aware of. And we can't just let the electrons flow from metal to metal. If not, we lose those electrons. So if they were in the same container, metal 1 and metal 2, and the electrons were flowing, and they just bounced from one side to the other, that would be a redox reaction. Like, that is actually a redox reaction, but we have no method to capture those electrons as electrical energy until we separate them into two chambers. Once we separate those two chemical entities into two separate chambers, and we make this external wire, like we see in this very top of this diagram, that is when we can capture those electrons to do work. So we can take those electrons and their potential to move, and we can say this can be captured to then run like an electrical system. What's current again? The unit for it? All right, this is amps, which is what, per what? Coulombs per second. Good. Okay, so there's a way that will vary itself, and it's based on a couple of factors. One, just the concentration, like in our cell setup down here. These are called cells, or half cells. But the cells have a solution that these metals are sitting in. The concentration will cause the current to vary. The surface area of this metal here, if it's got a lot of surface area, we have a lot of places to do the redox reactions with. We have a lot more current coming off. If it's got low surface area, not as many places to do the redox reactions with, not as much current. So that's going to cause it to vary. The resistance in the wires, just because high resistance, isn't that right? Physics people, what's resistance? Who's taking physics? Isn't that resistance? Ohms? Okay, so high resistance, low current. And current is also represented by the letter I. Okay, so if you have a lot of resistance in your wire, you're just not going to have as many electrons flowing per time. They're still flowing, it's just not so fast per time. So if I have a 100-gram sample of copper or a 1-gram copper sample, that will not cause my current to differ. It's more based on the surface area of that matter. Okay? So if you have your readings with you, you may have sketched one on your own as a part of your outline. You need to understand the anatomy of this galvanic cell. And the anatomy is, I'm going to probably just sketch one over here and keep it up here for the day. We always have an anode chamber and a cathode chamber. It does not have to go in order. Most of the time, I will always draw mine anode and then cathode just because it's in alpha order, but that is not always how it will look. So if I'm drawing it like this, and this is kind of, when you guys sketch your cells, it's not going to be beautiful like that. It's going to probably look kind of like this. So if I have my oxidation occurring on one side, I'll have my anode chamber. The other side I'll call my cathode chamber. Hopefully you're sketching as we go. And then in the anode chamber, what process is occurring? Oxidation. And in the cathode chamber, what process is occurring? Reduction. I like to say oil and rig. And then in our metal piece, in our other metal piece, these metal pieces are actually solid. They have to be solid. If not, it will not conduct electricity. So the metals must be solid. And if you don't have a metal species at all involved, you could have platinum to be used as a inert metal, but will still allow electrons to flow. So in our metal and metal, we'll also have metal ions. And metal ions are always cations, right? So they're floating around in the solution below. There's floating. And alongside of our chamber and chamber, we have a salt bridge. And a very common salt in our salt bridge is the one you can see on the board here. It's potassium nitrate. Notice I have that as an electrolyte look. It's not just potassium nitrate collectively together. It's potassium ion and nitrate ion. So those are going to be floating around in the salt bridge itself, and that's going to help really negate some of the charge buildup that begins to occur as these processes occur. So what I mean by that is that as the process of oxidation occurs, what's happening in the oxidation chamber? Electrons are lost, right? So the metal itself is giving up electrons, and the electrons flow through the external wire. And they flow and they hit the cathode chamber. So what happens to the charge of this poor metal as it continues to lose electrons? It becomes more, right, as you lose electrons, you become more positive. And as you become more positive, you are really wanting those electrons. There's a positive and negative attraction there. You don't want to continue to lose your electrons. But we want this battery to flow. We want the electrons to continue to flow. So the purpose of the salt bridge is that as it becomes more positive, what ion kind of matriculates this way? Nitrate, right? Nitrate begins to matriculate this way to say, hey, neutralize that charge, neutralize. So the positive charge stops building up, so the electrons are still willing to flow. It is really about charge buildup. So as I gain more electrons in the cathode side, what is the charge buildup over here? More negative. And as it gets more negative, it's like, hold up, I don't want any more negatives. Like, there's repulsion happening here. So who comes over here to neutralize this charge? Potassium. And that's through the salt bridge, and so they can kind of keep moving around to keep the battery flowing. So that's the general anatomy. Chamber 1, chamber 2, salt bridge, external wire. Electrodes are solids. Okay. Yeah, I have to do this first. Okay. So we have two examples here where this is not a galvanic cell setup. This is just a redox reaction. This is a flask 1, flask 2. And the example here shows you that copper solid, so you can see the copper solid here, and silver, it's like silver nitrate in here. You can see that with the copper solid and silver nitrate, there's a spontaneous reaction, and what is precipitated out on this copper? Silver, right? There's a lot of silver metal that is precipitated out on that copper piece of metal. But over here, I have copper solid and zinc, like nitrate, so zinc ion floating around. So why is this silver nitrate solution reacting with the copper, but the zinc nitrate solution is not reacting with the copper? Who's higher in the activity series? Who's higher? So zinc is higher than who? You got to give me some specifics here. So but zinc and silver are not in the same chain, like not in the same reaction here, guys. Okay, so zinc is higher. I'm gonna say higher, like you are saying. You're to move that means in a second. Higher than copper. So what does that mean about zinc? As we now know, the activity series has a special meaning to us now. Right, zinc is more likely to oxidize. So if you're high on the activity series, you're more likely to oxidize. And if you're low in the activity series, you're more likely to reduce. Right, there is a reduction, oxidation thought process behind the activity series. Okay, so zinc is higher than copper. Zinc's the one that wants to give up electrons, but zinc is in what phase here? It's in aqueous phase, right? It is zinc 2+. How would zinc lose electrons? What would that make its oxidation state? Higher than 2+, like 3+, 4+, 5+. Have we ever seen zinc that high? No, like zinc has a maximum. It is always a 2+. That is what it is. It always loses 2 electrons. So zinc cannot go any farther. Zinc is at its maximum oxidation state. It cannot be oxidized any farther. So this reaction just won't occur, period. Okay? So how about silver and copper? Compare them. Okay, so copper is more likely to oxidize. So what's its half reaction? Copper goes to copper 2+ and 2 electrons, and then where do those electrons go? Right, to silver. So it's likely to oxidize, meaning it's giving its electrons to silver. Silver's like, heck yeah, take that 1+, give me another one, and then what do I make? Silver solid, which you can actually see as a precipitate on that copper. So reactions occur based on their oxidation and reduction capabilities. They also have to be in the right, I say the right phase, but in the right oxidation state for those processes to even be able to occur. where this is a no reaction. So this is non-thermodynamically favorable, but this is thermodynamically favorable. This is technically like what we're talking about, but can we capture these electrons? In this chamber here, can we capture these electrons? No, there's no external wire. So there's redox happening there. It's like galvanic-ish in nature, but there's no ability to capture electrons because it's in a single cell. That's why we have to separate them into two. Okay? All right. So we're going to run out of time for the day, guys. So your homework is to continue reviewing. And, I'll give you back your electrochem test during intervention. Yes. And we're not going to be able to do 1 through 9 right now. Okay? But for the last little minute here, 2 minutes here. No, we have intervention. Yeah. Monday, the 18th, we'll be on intervention schedule as usual. Yes. Okay. So I'll pack up quietly and you're gonna watch my quick little video so you can actually see what's happening at the electrochemical level. All right, be quiet. Hush, hush. It's a 2-minute video. Here we go.
To
1-minute video. Okay.
the atomic scale and see how this cell operates. Here, at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and
We'll start with this
flow into the
tomorrow.
cathode.
At Joy, if you want to just put a tab on it when you turn your lab music in on Wednesday, I'll create it. Okay. No, just you can leave it there. I just wanted to make sure they had what they needed. Emily, will you cut the lights on for me? Thanks. Thanks, Joy.